This is a try it yourself exercise assignment final, and I want you to be able to go through the process in the overview. I will give you hints, but the follow along will be after the semester is over. So, in looking at this geometry, it really doesn't matter if you start with this lower kind of shape and then build up, or start with this back shape, front to back shape, and then build the lower. So when I look at this, let's see if we can zoom that up just a little bit. When I look at this, the bottom sketches, the slots, there's nothing really too complex there. The top with the funky shape, I would probably do some construction lines, block this out, make a rectangle, do some of the construction lines. On the next page is the geometry that they show on the interior. So, it's going to be to your advantage just to concentrate on this outside shape and worry about the interior as a second cut feature. The overall height is based on the 82 plus 15 and then getting to the 62 and making those tangent. When you see the limit dimensions, 16.018 to 16, we'll go with the for a hole, the maximum material condition is going to be the smaller number. So that is the most material that's available. If we cut a little bit more, then the hole gets bigger. That's less material. So we'll take advantage of those. And a little bit of discussion in the H7S6 is the fits for the hole in the shaft, internal and external features. So on that geometry, let's see, two holes, positions, the internal geometry, the circular. We haven't done a circular slot, but this is a good chance to experiment with the circular slot, which is basically a center point center point circle that we drag out, drag through, drag the slot out, and it will generate that geometry again with the limit dimension 10 millimeters, and the recommendation even for the going through the process and starting to think about stack ups and tolerances, because eventually those are going to become a lot more critical to our thinking and to our process. We're going to want to draw this at maximum material condition unless we talk to the machine shop, to the manufacturing engineer, to the mechanical engineer, and say, do we go to the mean? Do we go to the high side? Typically on a CNC type situation, I don't know that I would circular interpolate that with an end mill. I would probably ream the hole, so it'd be center drill, drill, and ream. This is a steel material. We're going to look at after the process. We're going to look at possibly changing some of these over to aluminum, a lighter weight alloy, and be able to utilize this as a flywheel and look at some of the mechanics using the motion functions in SolidWorks. Same with well, they're calling it a link, 95 millimeter link. So a couple of slots, again, limit dimension, radiuses. We've done this geometry before, so I don't expect it to be a real challenge. You can refer back to those previous videos. There are some additional geometries that we'd want to work with. This is still just a layout sketch, going through, placing the circles, getting your geometry associated, and getting the parts built. The pin and the bushings are pretty straightforward as far as sizing. So now we're on an external feature, and on an external feature, the maximum material condition will be the larger number, the 9995. So 10 millimeters minus just a little bit, and you look at the stack up 10 millimeters plus a little bit. So what we're looking for is a place where this is going to be a slip or a clearance fit and not end up in that crossover of a transitional fit or a press fit. So these being the same types of geometry, we can use the save as. You can, if you're comfortable with the configurations, you can go through and do the configurations. So at this point, don't worry about the H7G6. Be able to recognize these limit maximum material conditions. And worst case, if you pick one of the numbers and put it in there, it's still going to assemble, it's still going to go. But in design review, if you have to make a justification of the sizing and the clearances, this is where it's going to become a little more critical. So the other thing is, if we go to run a performance simulation, a Simulation Express FEA analysis on the assembly, those line to lines are a little bit easier to calculate. Telling the software that there's a gap and recognize that gap is still in contact becomes a little bit more computing power that is required. So I start off at least line to line, and then we have other tools that we can utilize to actually work on the stack up of tolerances and critical. And if we're making one of these, we can certainly hold tighter tolerances and be a little more precise with it. We always say when we go into looking at our manufacturing processes, we need to make 100 of these. It's a little more important. The programs become a little more efficient. Everything becomes a little closer under the microscope. We start making thousands, tens of thousands, or millions of these items. We want to know every detail, look for every penny, every cent that we can get out of this. So let's see, is there another page on this one, or does it jump over? So that was the end. So this is in the chapter on bearings and bushings. So there is a little bit of information. We'll take a look. You can take a look at the like the McMaster website and see what a standard purchased bushing or bearing would be. And I would think that this would be a bronze. They're calling it an SAE 3120. I would have to look at. I'm not that familiar with it, but I'm assuming that that is a steel. In the manufacturing ease of use, I would probably look at this being a oil impregnated bronze bushing, standard off the shelf replacement parts, and then a stainless steel shaft for the pin and the long pins. So, we're going to run through the same parts assemblies drawings. We'll pick up the videos with the drawing and give you some direction on applying those tolerances if you want. As usual, I'm not looking for a perfect drawing. I want the geometry I want you to understand the process of creating the geometry, creating the assembly, getting that into a working document in the drawing, and then as you refine the process and go through those iterations, and there will be many iterations, that spider web starts to come into view of all of these different influences and tools that we have available to us can bring it down to that document that can be utilized to manufacture these parts.